Okay, we're going to spend a couple of minutes going over a worked example that calls upon us to apply some of the concepts we've covered so far in class. In particular, the material from Chapter 2, dealing with hydrostatic pressures. From Chapter 2, and we'll be digging back a little bit further to go into an application of the ideal gas law, right, which is from Chapter 1. So the focal point of these ideas is going to be this drawing right here, which shows a simplified model of something like an ocean salinity probe. Okay, the idea here is there are lots of scientific instruments, an example being these what are called Argo probes, shown here, which are designed to float at the free surface initially. Then they'll be given some command that says dive to a predetermined depth, in this case about 2,000 meters beneath the ocean surface. Then they'll sit around and float around with the currents for a while before being told to reascend to the free surface, at which point they could transmit data back about things like ocean salinity, temperature, and currents. The Argo program, as this is called, Argo, is an international collaboration that has about 3,600, maybe 3,700 of these probes distributed all over the world, used to make distributed measurements of, as I said, things like ocean currents, salinity, temperature, both in around the world and at different ocean depths. Okay, so the way these work can be quite complicated, but a very simplified version is what's shown in this sketch here. It consists of a circular cylinder, right, which can be thought of as a tank, as a cylindrical tank, which is filled with some amount of air, and the remainder of which is filled with seawater, that is ballasting water, something that adds weight to it. So the way that this might initiate a dive, right, is by allowing air to escape through some valve at the top of the cylinder, which allows water to enter from the bottom, increasing the weight of the entire thing, making it negatively buoyant and causing it to sink. All right. Then when it chooses to reascend, or if it wants to remain neutrally buoyant, there will be some source of air, a tank of compressed air or something, which will be used to blow air into the top of the tank, increasing its pressure and driving some of the seawater out through a penetration in the bottom. All right. So, but the case that we're considering is this thing is sitting at the free surface and it has been given a dive command, right? It has just allowed air to escape and water to enter, but it has not yet begun to sink. It's at the instant before it actually begins to descend. So it could be thought of as a sealed cylinder except for this hole at the bottom, which allows water to enter and exit. So let's go over some of the geometric properties of this problem, right? The cylinder has a total height, which we're denoting as L, equal to 5 feet. It has a radius of 1 foot. And as shown here, we're going to assume that when it first begins its dive, it has a depth equal to 0.5 feet. And also a height of water within the tank of 0.5 feet. So unlike this picture here, if we can imagine getting rid of this water surface when both D and H are equal to 5 feet, that would look something like this, where the surface of the ocean is in line with the water level at the top of, or within the tank. At the start of the dive, we can assume that the air within the tank is at atmospheric pressure, right? So we'll say that P air is equal to P atmosphere. We're given that the specific gravity of seawater, right, is equal to 1.03, which we can use to compute that rho of seawater is 64 pounds mass per foot cubed. And we're given that, let's go ahead and move this over here to keep things balanced. And we're given that the density of air is equal to 0.079 pounds mass per cubic foot at sea level, right? Remember, air is a compressible gas. If you change its elevation, the pressure is going to change, and so will its density. So this is the state of affairs at the very beginning of the dive, as I said. And our task is going to be to find H, when D equals 1,000 feet. Okay, so let's go ahead and approach the solution first by computing what is very obvious from what we're given here. That is, we're going to go ahead and turn these given parameters into some geometric descriptors of this tank at the very beginning of the dive. So at the start of the dive, we can say things like, well, the volume of the tank, this of course it remains the same throughout the dive, is equal to pi r, oh my goodness, my handwriting's getting awful, pi r squared times L, which when we plug in values yields 15.7 cubic feet. We have the volume of seawater contained at the beginning of the dive, right, when H is equal to half a foot, is pi r squared H, 1.57 feet cubed. And from the known density of seawater, we can get seawater times density of seawater, the total mass of seawater contained at the very beginning of the dive, which is 100.5 pounds mass. All right. We can also compute the volume of air contained within the tank, which is going to be pi r squared, right, times the height of this cylindrical plug of air from here to here, which is going to be L minus H, right, which yields 14.4 cubic feet. And then finally, the mass of the air contained within the cylinder is going to be equal to the known density of air, right, which is given up here. That's supposed to be a 7. Known density of air times the volume of air contained within the tank, which will give us 1.11 pounds mass. Okay, so let's begin sort of analyzing the way that the problem is going to behave. Okay, what is our solution approach going to be? Now that we've written out everything we know a priori, how does the problem change once D is no longer equal to this initial value of 0.5 feet? So let's imagine we have the surface of the ocean here. We'll go ahead and define Z is pointing upward. At some depth beneath the free surface, we have our cylinder here. So this is hanging out, or in the process of descending. It is at some depth D. And then inside of that cylinder, we have some volume of seawater, which constitutes another free surface. At the ocean surface, at sea level, right, we've been told that this pressure is atmospheric pressure, and inside of this tank we have air, which is at some unknown pressure. So at this point right here, at this interface between the water and the air inside of the tank, we can go ahead and write the pressure of the air, right, at that point, equal to, using our the equations of hydrostatic pressure variations. Here, let me go ahead and write this. Remember, we have that P at some depth beneath the free surface is going to be equal to what? P atmospheric minus rho g z. Right? This comes out of our hydrostatic pressure variation, which tells us that the pressure varies linearly with increasing depth. So the pressure at this point, right, this interface, can be written as P air is equal to P atmospheric plus rho C water times G times D, right? That gets us the pressure at this point, at the very bottom of the tank, minus H, which gets us the pressure as we travel back up this distance H inside of the tank. Right, so here's one expression for the pressure inside the tank created by simply the hydrostatic pressure variation. This pressure, of course, right, this is the pressure created by the weight of the water. It's balanced by the pressurization of the air contained within the tank. And the way we approximate the variation of the pressure within the tank is using the ideal gas law, right? So we have the ideal gas law, which tells us that the pressure of the air is equal to the density of the air times our gas constant times our absolute temperature. If we do some rearranging, we can write this to say that P air over the density of air is equal to simply RT, which is going to be constant if we assume isothermal compression. That is, if we can assume that this air is compressed without T here changing temperature, or without the value of T changing, then P over rho is going to be a constant quantity. Meaning that if we can go ahead and find that constant, RT, then we can plug that into this version of the equation right here to find the pressure of the air due to gas compression, which will then balance the pressure at this interface created by hydrostatics. All right, so how do we go ahead and find this value of RT? Well, if P air over rho air at a depth of D is equal to RT, which is a constant, that means because of that constancy, it has to also be equal to P air over rho air at sea level, right? And if you'll bear with me as we scroll back up here, if we look back up here, we are given both the pressure of air and the density of air at sea level in the problem statement. Meaning we could directly compute this constant as P atmospheric over our 0.079 pounds mass per foot cubed, which ends up leading us to a numeric value of 8.674 times 10 to the 5th feet squared per second squared. Okay, so at this point, what have we accomplished? Well, we've pretty much performed a brain dump of different ways of getting pressure, right, from hydrostatics, from the ideal gas law, and we plugged in some known expressions here in order to calculate the value of RT. So where does this leave us? Let's go ahead and do sort of a roll call of our equations and unknowns. How many equations do we actually possess at this point? We have we have our hydrostatic equation, right, which says that P air is equal to P atmospheric plus gamma seawater D minus H. So there's number 1. And we have from the ideal gas law that P air is equal to RT, which is a known constant, right? Has this value right here, times rho air. Okay, so we have 2 equations. Now let's count up how many things we don't know, right? How many unknowns do we have? Well, we have, for starters, the pressure of air itself, okay? That's an unknown quantity. We know the atmospheric pressure. We know the specific weight of seawater. D is specified in the problem statement, right? We're going to go ahead and say that D is equal to 1,000 feet. So that is also known. We don't know H. We know RT from up here, but we don't know the density of the air at the depth of D equals 1,000 feet. So, unfortunately, we have 3 unknowns, right? Meaning that if we want to solve for them, we need one more equation. Now, where's that equation going to come from? Well, let's go ahead and pick out the density of air, right? We know that the density of air can be defined as the mass of air over the volume occupied by air, right? Do we know either of these to begin with? Oops. Well, we could compute the volume of air by recognizing that, right, we wrote it up here, right? The volume of air is pi r squared times the height of L minus H, which remains valid, right? Pi r squared L minus H, where H we don't know any longer, right? That's still an unknown, but that unknown is already accounted for up in equations 1 and 2, so we're not adding any additional unknowns there. And the mass of air, I want you to think about that for a second. Where would we get the mass of air contained within the tank? Well, that's also provided at the beginning of the problem, right? Mass of air at the start of the dive is 1.11 pounds mass. Now, is there any good reason that should change as the as this probe dives through the ocean? Hopefully, you're shaking your head and saying to yourself, "No, that shouldn't change," which is accurate. Remember, I said that once this begins its dive, it is for all intents and purposes the top is sealed, right? The mass that is contained at the start of the dive remains in the tank. It will be compressed by the increasing pressure, but the number of molecules remains the same. So we can simply take this known mass right here and carry that all the way through the problem. Mass air, which is a known quantity. So at this point, we've eliminated rho air from our equations, right? If we substitute this in right here, this will give us RT times mass of air over pi r squared L minus H. So our unknown here remains H, leaving us with 2 unknowns, P and H, to be solved for using these 2 equations. So what's really great about this is we now have 2 separate expressions for pressure, which are functions of only H, right? Because D is specified here and everything else is fixed. RT is a constant, mass of air is constant, pi r squared is fixed by the problem geometry, L is a piece of the problem geometry, gamma seawater is whatever nature decides it's going to be, and the atmospheric pressure is fixed. right? The only variable on the right-hand side is h. So if we want to find h within the tank, the idea is we're going to plot pressure. We're going to plot both of these equations to plot the pressure as a function of h and find the point at which they intersect. Okay, so if we create a set of axes here, on the x-axis is going to be h with units of feet, and it's going to have values of 0, 1, 2, 3, 4, and 5 feet, right? H can't go beyond 5 feet because that's the height of the cylinder, right? So this is the upper limit on h. And let's go ahead and plot equation number 1 first. Okay, so equation number 1 we'll plot with a blue line. And what this is going to look like is a linearly decreasing curve. Right, this is P atmospheric plus gamma seawater D minus, we'll say 1,000. Oh my gosh, let me write this a little bit larger. P atmospheric plus gamma seawater times 1,000 feet minus h. All right, and our second equation, number 2 here, is going to, we'll go ahead and plot this one in green, right? RT times mass of air over pi r squared L minus h is going to look something like this. So the point, this is equal to RT mass of air over pi r squared L minus h. So the point at which these two lines cross, right, is the point at which the pressure due to the hydrostatic pressure distribution in the seawater balances with the the gas pressurization that we've attributed to the ideal gas law, right? So we just simply find that point where they intersect and project down, and here we have, right, this will give us h at d equals 1,000 feet. And so if we go ahead and plug in, right, all of the numbers that we've computed as we progress through this problem, I've tried to save some paper here. We're going to find that h is equal to approximately 4.85 feet. So if we take a moment to appreciate this, right, what this is telling us is 4.85 feet. Right, as this cylinder moves deeper and deeper and deeper into the ocean, the pressure continues to build up, which compresses the air in order to balance out the hydrostatic pressure and create a stable surface. But by the end of its 1,000-foot dive, what started out as a 4.5-foot tall column of air has been reduced down to 0.15 feet, which is 1/30th the original volume. So it's compressed this initial 14.4 cubic feet down to 1/30th of that volume, while the air retains all of its mass. So what we get from that is, as this thing goes deeper, right, its net density is going to increase because the water level is rising, and this lighter gas is getting more and more compressed and more dense as a result. It's going to begin to, its tendency to sink is only going to increase with added depth. So if this thing, for example, if it's if it's air valve, right, or if it's air tank that it uses in order to blow air back into this and drive the water level back down to cause it to rise. If there's a clog in this line or something blocks this compressed air line, this probe is gone. It does not self-recover. It does not find an equilibrium and hang out in a neutrally buoyant position. It's an unstable system. It's going to continue to sink, and its tendency to sink is only going to get more and more pronounced as it goes deeper. So hopefully this has been a not overly confusing overview of how we can use hydrostatics and other means of calculating pressure distributions. Right, we have an incompressible fluid and a compressible fluid in equilibrium, and we've applied it to calculating the tendency of some engineered system to float or sink. I'll be posting these notes up on the course website, so if you had trouble following along in this video, you can find them there in PDF format.